All right, 10.3, it's called More on Limits. So, obviously, first and foremost, we have the definition of a limit at A. So, when we write the limit as x approaches A of f of x is equal to L, we mean that f of x gets arbitrarily close to L as x gets arbitrarily close but not equal to A. So next we're going to have 7 properties of limits. So if the limit as x approaches c of f of x and the limit as x approaches c of g of x both exist. Does anyone else always try to put an E on the end of both?
Yes.
Like literally every time I put one on there, I'm like, what is happening? Yeah. I do it all the time. Like I literally was just like.
Yeah, I like to connect the E.
Especially like the both exist, like it just is gonna run together, and I was like, yeah, okay, we need to fix that. All right, so first we have the sum rule, which says that the limit as x approaches c of f of x plus g of x is equal to the limit as x approaches c of f of x plus the limit as x approaches c of g of x.
We haven't seen g of x for a while.
So basically this just says if two things are being added together, we can split the limit into 2. And vice versa, obviously. The difference rule is going to work the exact same way. So the limit as x approaches c of f of x minus g of x is equal to the limit as x approaches c of f of x minus the limit as x approaches c of g of x. Next, we have the product rule, which is that the limit as x approaches c of f of x times g of x is equal to the limit as x approaches c of f of x times the limit as x approaches c of g of x. So maybe no surprise that when things are being added, subtracted, or multiplied, we can just split them. And it's just the limit of each one individually and then their respective sign. We have then a constant multiple rule. Which says that the limit as x approaches c of k times g of x is equal to k times the limit as x approaches c of g of x. So what that means is that basically I'm taking a number, say 3, and multiplying it by the entire function g of x. And so it doesn't matter if I have it inside and I have already multiplied it through and then I take the limit, or if I take it out, take the limit, and then multiply it by that, your answer is going to be the same either way. It actually makes it easier to take it out if there's a common thing, take the limit, and then multiply it through, in my opinion. Next, we have the quotient rule. So this is the limit as x approaches c of f of x over g of x. And probably no surprise, this is the limit as x approaches c of f of x divided by the limit as x approaches c of g of x. Now, this is obviously something to note, provided the limit as x approaches c of g of x is not equal to 0, because then that would make it undefined. All right, next we have the power rule, which is the limit as x approaches c of f of x raised to the n is equal to, it's in parentheses, the limit as x approaches c of f of x all raised to the n for n a positive integer. So it's saying if you were to raise your function to a power, then take the limit, or you were to take the limit, then raise it to a power, you're going to get the same answer either way. But sometimes it being written one way or the other makes life easier. And so that's why. And obviously, like, there's still one more rule, but a lot of these rules could be combined into one potentially, depending on how it, you know, like the power rule could be in combination with, say, the quotient rule. And so it may make it easier to rewrite something or whatever first. All right, and then the last one of those is the root rule. I've written rule so many times I feel like it's spelled wrong now. The limit as x approaches c of the nth root of f of x is equal to the nth root of the limit as x approaches c of f of x for n greater than or equal to 2, a positive integer, provided the nth root of the limit as x approaches c of f of x and the limit as x approaches c of the nth root of f of x are real numbers. So basically, like, couldn't have a negative under the radical, because then that would cause it to be imaginary. All right, now this is a limit that you just need to memorize. The limit as x approaches 0 of the sine of x over x is equal to 1. And you're probably like, well, why do I need to memorize that? Because it will make your life a lot easier in solving other limits in the future by knowing that.
Can you scroll up? My number is off, so I think I'm missing one, but I don't know which one. It's not this too. Okay. It's product rule.
Which one is it?
Product rule. Okay, I got you.
Now, there are some things with limits of continuous functions, but there's not really any notes about that. It's just like going back to knowing that a function is continuous, and that's all the way from like chapter 1 of just knowing that. But basically, all that means is you can use all the rules that we've just, properties, whatever, that we just had, and they apply. So. All right. One-sided and two-sided limits. Before I give you the actual theorem that goes with that, I'm going to explain left-handed and right-handed limits first, and then we'll do the theorem that goes with this information. So a left-hand limit is the limit as x approaches c, and then it's got a negative sign basically in its exponent. Okay, that just means from the left of f of x. And so we read this as the limit as x approaches c from the left. And then the right hand, anybody want to guess what's different about the right hand one? The limit as x approaches c from the right, which is positive, of f of x. And it's read the limit as x approaches c from the right.
Bless you.
All right, so then the theorem that goes with this, okay, the theorem is for one-sided and two-sided limits, says a function f of x has a limit as x approaches c if and only if, so remember IFF is if and only if, the left hand and right hand limits at C exist and are equal. That is, so in symbols, the limit as x approaches c of f of x is equal to capital L. That means just the limit value. If and only if, remember that's a two-sided arrow. It's like going all the way back to geometry. the limit as x approaches c from the left of f of x is equal to L, and the limit as x approaches c from the right of f of x is equal to L.
This brings me back to geometry when we had to write our postulates and our postulate field.
Oh yeah.
True.
Awful.
And so some of this will also allow us to find points of discontinuity in a function using this information. So basically, if you were finding one and two-sided limits, if your limit of your left hand and your limit of your right hand are not equal, then the entire limit does not exist. So that's what this is basically saying. It'll make more sense when you see an example of it. Let's see. All right, the next thing are limits at infinity. And so there's going to be two of these. So when we write the limit as x approaches infinity of f of x is equal to L. So remember, this is what we've kind of seen this before. This is when I was like, imagine that x is just getting really, really big. What's happening? We mean that f of x gets arbitrarily close to L as x gets arbitrarily large. Bless you. We say that f has a limit L as x approaches infinity. And then the other one, when we write the limit as x approaches negative infinity of f of x is equal to L, we mean that f of x gets arbitrarily close to L as negative x gets arbitrarily large. So we say that f has a limit L as x approaches negative infinity. It's kind of smushed in there. I think that's all that we need to do for this.